Okay, this is the video for Unit 4, Lesson 2. We're looking at polynomial functions. We're going to be analyzing the functions, more looking at graphs and looking at the equation or the function and seeing what we can figure out about it. Okay, and then next class we're going to apply that to actually graphing a function. All right, so this first box here, this should be a review of what we did in quadratics. Okay, this is all in general terms. Okay, we'll have more practice with this in the classwork. Okay, but this is all if f is a polynomial function, or for any polynomial function, all four of these are true. Okay. Okay, so if a is a zero of f, or if a is a solution or root, x minus a is a factor. Okay, here we go again. X equals a is a solution. Make sure 0, root, solution, it's all the same thing. You're looking for that value of x when y is 0. Okay, and then x-intercept is written as a point. Okay, all of these things are related. Okay, so before I move on, let's tie this back to quadratics. How many real solutions exist if there are not any x-intercepts? All right, x-intercept means the point exists on the graph, okay, which means it's real. Okay, if there aren't any x-intercepts, there are no real solutions. Okay, we're going to continue to look at real and imaginary solutions for polynomials. We're going to obviously expand on what we did with quadratics. Okay, remember the fundamental theorem of algebra, where the total zeros, not to be confused with distinct zeros, more on that in a bit, total zeros is the same as the degree of the function. Remember, we talked about that in lesson 1. Talked about the degree is whatever the highest exponent is. Okay, you write that in standard form with the exponents in decreasing order. So the highest exponent is the degree of the function. That's how many total zeros they're going to be. They could be real or imaginary, or real plus imaginary are your total zeros. Okay, so let's look at this graph down here. This is actually a cubic function. You can see that because there's two terms. All right, let's actually talk about the roots and zeros for this. This intersects the x-axis at x equals -2, -1, and +2. Okay, so remember we write the x-intercepts as points. All right, so if -2 is a solution, that means a factor is x plus 2. -1 is a solution, the factor is x plus 1. 2 is a solution, the factor is x minus 2. Okay, so hopefully that's a review from quadratics, but it's important for any polynomial, which includes quadratics, to be able to do that so we can go back and forth between the function and the graph and all the other characteristics. Okay, so what we want to add to this is this concept of multiplicity. Okay, as I mentioned before, we have distinct zeros. We've used this term before. A distinct zero is if you have the graph cross the x-axis at any point, that is one distinct zero. Okay, but let's say we have the graph just touch at one point like that, or like this. Okay, on the left here, this is a linear function, or this looks like this is crossing the x-axis. It looks like a linear function. Okay, remember in terms of polynomials, linear function is just like 2x plus 1, 2x plus 4, and so on. Okay, it's x to the first power, but we don't write the 1. Okay, so this resembles a linear function as it crosses the x-axis. All right, so what we say is this has a multiplicity of 1. Oops, I already wrote multiplicity. A multiplicity of 1 because the way it crosses the x-axis resembles the function that has a degree of 1. Okay? So while this is one distinct 0, it's also one total 0 at this particular point. And this could be going up. You could have it crossing like this. Okay? Both of these zeros have a multiplicity of 1. They're each distinct zeros, and it's one total 0 at each x-intercept. All right, let's look at this next one. So you've got, these are just parts of a bigger graph. Okay? You could have it be, this is, again, this is just a part of the graph that touches. There could be more to the graph out here. It could come up and do this and something like that. But we're just looking at that green part that touches the x-axis or is at the x-intercept, or this black part here. It touches the x-axis at one point and bounces off. Okay? It looks like a quadratic function when it touches the x-axis. Now, quadratic is a second degree polynomial. Okay? So each of these distinct zeros have a multiplicity of 2. Okay? So for each distinct 0 that has a multiplicity of 2, that counts as 2 zeros. Okay? But is one distinct 0. Okay? Multiplicity of 2 just increases how many zeros we're talking about. Okay? This next one, we haven't done these yet. This is a cubic. We're going to do more of these. Okay? This point here, it's called an inflection point. Okay, you don't need to know any more about it than that. Okay, but this really counts as 2 turns. There's one of these in the classwork that we didn't talk a lot about in the notes, but this is an inflection point. But this is crossing the x-axis in what appears to be a cubic shape. Okay? Cubic is a 3rd degree. So each of these zeros would have a multiplicity or appears to be a 3rd degree function, or resembles a 3rd degree function. They'll have a multiplicity of 3, meaning each of those are one distinct 0, but count as 3 total zeros. Okay? Again, each of these examples on these graphs are just part of a bigger graph. All right, there could be other curves going on, but we're just talking about when it touches the x-axis, what does it look like? Okay? All right, so let's try to apply that on the next page. Okay, so we talked a little bit about turning points last time. Okay, you see the term relative or local maximum and minimums. All right, all that means is it's where the graph turns, or they are turning points. Okay, so this graph down here that we're going to look at, this point here and this point here, those are relative or local maximums and minimums, because where they are, that's the highest point for that location. this one here. But the graph keeps going this way. So it's not the maximum, the absolute max of the graph. It's just a local max for that location. It's relatively the highest point for where it is, but it's not the highest point of the whole graph. Same with this one. This would be a local minimum. This is a local min. Because where it is the lowest point, but as you look at the rest of the graph, this down here is the absolute minimum. Because we can tell that there's nothing below it. Okay. There's something below this point, but it's not the lowest point of the whole graph. All right. So we'll get to that at the bottom here when we analyze the rest of this graph. Okay, so let's just look at it and kind of combine what we did last class. So look at the degree of the function. Is it even or odd? Well, remember, if they're both going in the same direction at the end, that means it's an even function. If they were going different directions at the end, that would be odd. All right? The whole graph is opening up. So the leading coefficient has to be positive. If it was opening down, it would be negative. All right, let's look at the zeros. Again, you could also say roots or solution. All right, so this first one is -1, and then +1 and +2. Those are my zeros. All right. Let's look at the multiplicity of each zero. This first one, -1. This is crossing the graph in the shape of a cubic. So we say that that 0 has a multiplicity of 3. Okay? At 1, it's crossing it in what looks like a linear shape. I know this is tricky because of how the graph is laid out, but that is a linear shape as it crosses the x-axis. So that is a multiplicity of 1. The last 0, x equals 2, that's coming down and then bouncing off the graph. It looks like a quadratic as it touches the x-axis. A quadratic is a second degree polynomial. So if something has the shape of that as it crosses the x-axis or touches the x-axis, it's got a multiplicity of 2. Okay, so how do we write that as factors? Okay, well the 0 is -1, so the factor would be x plus 1. The multiplicity is 3, so we write that. Okay, the multiplicity affects how many times that factor occurs in the whole function. Okay, the next 0 is +1, multiplicity of 1, x minus 1 to the first power. But we don't have to write that 1. I'm just leaving it up there so you can compare it to the others. 2 would have a factor of x minus 2. But that 0 has a multiplicity of 2, so we square that factor. Okay? So if we say write the factored form, just take these factors. You write f of x or g of x, however we tell you to write it. You write the highest one first, and then go in descending order. You don't need to multiply all these out. We're not going to ask you to do that for something this big. Now the question is, what degree is this function? Okay, look at the multiplicities. That will tell you the total zeros. There are 3 distinct zeros here. But since they have different multiplicities, it's going to increase the total number of zeros. So if you have a multiplicity of 3, that counts as 3 zeros. A multiplicity of 1 is 1 0. A multiplicity of 2 is 2 zeros. So we have 6 total zeros, which according to the fundamental theorem of algebra we did in the first lesson, means this is a 6th degree polynomial. if you look at the turns here, you've got 1, 2, 3 turns that are obvious. This inflection point counts as 2 turns. So there's 5 turns, technically 6 degree. Okay. All right, so let's get to that local max and local min that we talked about. These aren't going to be exact, but we're going to round a little bit. All right, so let's look at that local max that I circled up there in red. That x value, we'll call it 1.5. And that y value, we can say it's 2. So the local max occurs when y equals 2 and x equals 1.5. The local min occurs at x equals 2 and y equals 0. You won't have this on your sheet. I'll go back and fix this on your sheet. That's just an extra. I copied too many spaces there. Okay, so those are your local max and local min. You should be able to identify that. We'll practice also on the calculator, finding zeros on the calculator, typing in the polynomial function, using the calculator to find zeros, using the calculator to find local max and local mins. Okay, so we'll practice using the calc in classwork. Okay, but this way you know at least what you're looking for. Okay? So that's analyzing the graph, everything that we've talked about to this point through lesson 1 and lesson 2. All right, we'll have lots more practice with that in the classwork. All right, so the last thing is, let's write a polynomial function in factored form and state the degree given zeros. So there's something we got to remember here. You see a radical, you see an imaginary, okay? So remember with imaginary, if 3i is a root, that means negative 3i is also a root. Okay? The same applies to this square root of 5. Okay? Radicals also come in conjugate pairs. So if negative root 5 is a root, that means positive root 5 is a root. Okay? So, how do you get that in factored form? Well, just change the signs to the factors. For the 3i's, it's x minus 3i, x plus 3i, times x plus root 5, x minus root 5. And then this 1 happens twice. So it's x minus 1 times x minus 1. Whoops, I don't need that squared yet. So we're just doing this in factored form, but we don't want any radicals or i's. So we're just going to multiply these two together. All right, so remember when you multiply these conjugate pairs, that middle term is going to cancel out. You're going to get x squared minus 3i times x plus 3i times x minus 9i squared. The I squared is going to change the sign, so it's going to be plus 9. These cancel out. I get x squared plus 9. Same deal with this one. X squared plus x times root 5 minus x times root 5 minus, remember, square root of anything squared is just that number. Okay? So these cancel out and we get x squared minus 5. Okay? So in factored form, we'd write f of x equals x squared plus 9 times x squared minus 5 times x minus 1 squared. Okay? We'll get plenty more practice in classwork. We can talk about any concerns you have about this, but go ahead and practice this one over here to the right. Pause the video, try that, and check your work. Okay, one thing we forgot to do in the example was talk about the degree. So you can just add up the x's here. There was an x squared, another x squared, and this would multiply to be x squared. So this is a 6th degree. Number 2, you'd get a 7th degree. You have a -3, which does not have a conjugate pair, the root 3, which does have a conjugate pair, and the 2i, which has a conjugate pair. Okay. So in the blue here, we have all your factors, and then you have your function here in red. Okay, again, we got plenty more chance to practice that in class. You'll use these notes to help you with that. Okay, so make a note of any questions, and we'll see you in class.